Here is the grand conclusion of the topics we've already looked at. We're going to take the idea of spanning and the idea of linear independence and put them in a blender and come up with the idea of having basis sets for vector spaces. We're going to look at what is a set of basis vectors for a particular vector space and how do we determine if some set happens to form a basis for the vector space or subspace they live in. So we've already set up the threads we need. The collective span of a set of vectors, we know what that means now. It turns out that's automatically a vector space. If we have all of the possible linear combinations of a set of vectors, when we take them and add a couple up or multiply one by a scalar, we get a new thing which would still be a linear combination of that set of vectors. So the span of a set of vectors is a self-contained whole. It turns into an actual subspace. Now, if a spanning set, which generates some vector space, which is its total span, if the spanning set happens to be linearly independent, then that means we can't dispense with any of them and reproduce the same space. So if a spanning set is linearly independent, no set of fewer vectors could span the same space. Now, a set of more vectors could span the same space, but at least one of them would be redundant because of the linear dependence. So a set which spans some particular subspace and which is also linearly independent is a pretty efficient set of vectors, and it's called a basis for that space. It spans the space, and the number of vectors that you have is the magic number. You can't dispense with one and get the same space back, and you can still get the same space with more vectors, but those more vectors are redundant. And so this magic number, which is the number of vectors in a basis for a space, is the dimension of the space. And the job of this basis set is that any vector in the space can be written as a linear combination of those vectors. You already know some basis vectors. You may not have called them basis vectors, but nonetheless, you know them. Take two-dimensional space, or R2. The unit vectors 1, 0, and 0, 1 are a basis for this space. You know that any vector in R2 can be written as a linear combination of those two things, and those two are linearly independent. Similarly, for R3, the standard unit vectors are a basis for R3, and the dimension of typo, and I'm too lazy, I'm not going to start this recording again, so let's just live with that typo. That's just supposed to be the boldface R squared. Some of the coding snuck in where it shouldn't. Shame on me. But anyway, those three unit vectors are a basis for R3. We can't get away with one less, and adding one more would be silly. And so the dimension of R3 is 3. Switching to a different kind of vector space, look at the space of all polynomials of degree 2. We will denote that as bold P with a 2 as a subscript. So P sub n would be all polynomials of degree n. So P2 is the space of all polynomials of degree 2. And you know, or you can figure out, that the vectors 1x and x squared would be a basis for that set. Their collective span will be all of P2, and we can't throw one of them out and get the same space back. And any more than those three would be silly. And so the dimension of this space is 3. Could you design a basis set for the space of all 2 by 2 matrices? And if you can, what would be the dimension of that space? I'll let you think about that. We'll get an answer somewhere down the line. So let's put these ideas together and do some quick thinking about the idea of basis sets. So, two vectors, 1, 0, 2, negative 3, 1, 1. They will have a spanning set, the collection of all of their linear combinations. That collection, that vector space, would be within R3 because these two are three-dimensional vectors. The dimension of this space would be 2 because now there's 2 basis vectors for that space. These two vectors themselves cannot generate all of R3, but whatever their spanning set is will certainly be a subspace of R3. Those two vectors are clearly linearly independent because one isn't a multiple of the other, so it's a spanning set for their subspace. They are linearly independent. The dimension of this subspace is 2. Change it up a little bit. Here's a new spanning set. Their collective span will still be a subspace of R3, but this time the dimension of that space will only be 1 Do you see why we changed it? It's because in this spanning set, the second vector is just a multiple of the first vector. It's redundant. So this is a spanning set, but it is not linearly independent. A linearly independent set that produces the same subspace would only have the vector 1, 0, 2 in it. And so the dimension of this subspace is 1. Okay, here's the standard basis set you know about for all of R3. Any other set of 3 linearly independent vectors in R3 will also span R3 and will also then be a basis for R3. So basis sets aren't that special because there's an infinite number of basis sets for R3, for example, but some of them are better than others. And why they're better, that's a whole other thing. We won't get into that just yet. Now, if you have a set of vectors which is a candidate basis for a vector space, how do you show that it is? Well, we're going to check 2 things. First of all, we have to show that the vectors in question span the space we're talking about. Otherwise, they can't be a basis set for the space, which means, of course, that any vector in the space can be written as a linear combination of this candidate basis set. Now, in past examples, we've looked at the question, here is a vector, here is one vector, is it in the span of these other vectors? We know how to answer that. We've built the system of equations and so on. Okay, so we've answered this question for one vector. Notice that it's changing slightly because now we want to be able to show that any vector from our space can be written as a linear combination. That's going to be a slight twist, but we'll still be able to handle it. Secondly, to show that a candidate basis set for a space is in fact a basis, having shown that it spans the space, we also have to show that the vectors are linearly independent. Otherwise, we have too many of them and it won't be a basis. Now, setting up the check for linear independence is exactly the same as it was in the last set of slides, so you'll know how to do that. So here's an example. 3 vectors, 2, 0, 1, 1, 1, 2, and -2, -1, 0. Are these a basis for R3? Well, first we have to show that they span all of R3, meaning that we can show any arbitrary vector out of R3 can be written as a linear combination of that set. Okay, here's the setup for that. On the left is your linear combination of the 3 vectors, and on your right is this randomly grabbed vector from R3. We do not want to put specific numbers in for W1, W2, W3, because then we're only asking, is this one vector a linear combination of the other 3? Written now, we are checking, can any vector from R3 represented with the W's be such a linear combination? We can still build that system of equation that comes out of that, right? So here is the system of equations that comes out of it in matrix form. The unknowns are the A's, and the W's are playing the role of whatever vector we happen to have selected that we want to see is a linear combination of the other 3. So keep that matrix structure in mind. And we're going to go to the other question here, which is the linear independence question. Are these 3 vectors linearly independent? Well, as before, the way to check is we take a look at the linear combination of them and see what it takes to produce the 0 vector. We hope that the only way to produce the 0 vector out of this linear combination is the case when B1 and B2 and B3 all have to be 0. So that's what we're looking for. Here is the matrix version of that system of equations. So put these 2 things back together. Here is the question of spanning. Here is the question of linear independence. Can we show that there are solutions to both of those at the same time? Look at the coefficient matrix for each. It's the same. Now we know about solving systems of equations with matrices. If that coefficient matrix has an inverse, then both of these systems will have a unique solution. So in the top system, we will have shown that no matter what W1, W, and W3 are, there will be a unique solution for a linear combination building that vector. And in the second one, if the coefficient matrix has an inverse, we will be showing that the only way to produce the 0 vector is for the B's to all be 0, meaning linear independence. So you know how to find inverses. We're not going to repeat it. This is cool because we get to solve 2 problems with one shot. So again, running through it, we know that we have a basis set already for R3. It's a great basis set. There's nothing wrong with it. In fact, it's the best basis set you can have, but just for funsies, we're trying to decide if these other three vectors could act as a basis for R3. We've decided that that is determined by whether or not this particular matrix has an inverse. You've already done this. So you could find out, as I have, that this matrix does have an inverse, and that means that these three vectors span all of R3, they are linearly independent, and therefore they are a basis for all of R3. Could these be a basis for R3? Well, no. These are four-dimensional vectors. We could not write three-dimensional vectors with linear combinations of them. So get out of here. Could these four vectors be a basis for R3? No. We know that the dimension of R3 is 3, which means basis sets can only have 3 vectors. This set has 4 vectors. So they have to be linearly dependent. Now, the span of these 4 vectors could very well be all of R3, but their span being R3 doesn't mean they're linearly independent. You have to check those things separately. These would not be linearly independent, so they can't be a basis. Get out of here. Could these two vectors be a basis for R3? Well, no, there's not enough of them now. Any basis of R3 has to have 3 vectors, so get out of here. How about these three? Not quite so obvious. They have a chance of being a basis, and so let's run through the procedure one more time on these just to get it down. We're going to check whether these three are a basis set for R3. So we have to check that they span all of R3 and that they are linearly independent. So the first blob there is what we get when we take a linear combination of those 3 vectors with coefficients a1, a2, and a3 in the linear combination and produce a randomly grabbed vector out of R3. Can that happen with unique solutions for the A's? Well, that system will tell us that. The second blob is checking for linear independence. We've built a linear combination of those 3 vectors with coefficients b1, b2, and b3, and we're checking out what does it take for that linear combination to produce the 0 vector. We hope that the only way that can happen is for b1, b2, and b3 themselves to be 0. So we would really like both of these systems to have unique single solutions, and we know that they will if that common coefficient matrix does have an inverse. Well, it does. And so those 3 are a basis for R3. And here's a bonus. Knowing that these 3 vectors are a basis for R3, we can actually go back and, for any vector that we've happened to grab, we can find out the magic numbers that will make a linear combination of the 3 basis vectors turn into the vector we want. So let's just pick the vector -1, 2, 5. If we plug those in for the w's, we can then solve the system and get that the coefficients of the basis vectors that will build the vector -1, 2, and 5 are 3, -4, and -7. And that means that we have identified the components of w with respect to those basis vectors. Let's switch systems and look at P2, the space of all polynomials of degree 2. We've already looked at how 1x and x squared is a basis for that space, meaning the dimension of this space is 3. So could the set shown now, which is 3, 2x, x squared, and 1 plus x be a basis? Well, no. There's too many vectors / polynomials in that set. The dimension of this space is 3, so any basis set can have 3 and only 3 members. So 1 plus x and x squared, could that be a basis? Nope, there's not enough of them there. How about 3 and 1 plus x and 2x squared? That's got a chance. So let's take a look. To see if that set is a basis for P2, we have to make sure it spans all of P2 and is also linearly independent. So here are 2 equations which check out these 2 things. The top equation is taking a linear combination of the 3 potential basis vectors and using them to try to build a randomly grabbed member of P2, which is capital A plus bx plus cx squared. What does it take for that to happen? Can we do it for a unique set of A1, A2, and A3 regardless of what's on the right-hand side? If so, this is a spanning set. The second equation is looking for linear independence, taking a linear combination of the 3 vectors in the potential basis set and asking what does it take for these in a linear combination to produce the 0 vector. We hope that the only way that happens is for b1, b2, and b3 themselves to be 0. And if so, we have linear independence. Here are the systems of equations that come from those. So match up the coefficients of x squared and x and the constant term in the top equation, and match up the coefficients of x squared and x and the constant term in the bottom set. And here are the two systems of 3 equations and 3 unknowns that we get. They both have the same coefficient matrix. Looks like this. This matrix does have an inverse. You know how to find out, so I don't need to show you. But that matrix does have an inverse. So, again, backing up, those two systems of 3 equations and 3 unknowns would both have the unique solutions we're looking for, and therefore our vectors span P2, they are linearly independent, they are a basis for P2. And there you go. So finding basis sets for vector spaces, a combination of do the vectors in this potential basis set span the entire space? Are they linearly independent? 2 questions we know how to answer. We have to answer them both yes, and if so, you found a basis. So go forth and solve lots of systems of linear equations.